In this module, you'll move from "I've only used GPUs" to confidently running models on Google Cloud TPUs. You'll provision TPU hardware, adapt existing TensorFlow or JAX code, and run it efficiently on purpose-built ML infrastructure. Choosing a TPU generation is really about trading cost for scale. TPU V2 and V3 are your budget-friendly workhorses. Ideal for standard vision or NLP models, smaller parameter counts, and experiments where you'll run many trials. TPU V4 and V5e target production scale. They deliver much higher flops and bandwidth, support large language models, and can be combined into multi-chip pods, well suited for high throughput and enterprise workloads. One major way TPUs differ from GPUs is in how they avoid network bottlenecks. In older setups, your training script ran on a separate CPU VM and sent commands over the network to a remote TPU. Each step paid a latency penalty, and debugging felt slow and awkward. With modern TPU VMs, you log directly into a host that sits next to the TPU chips. Your code, frameworks, and the TPU runtime all live on that VM, cutting latency and making setup and iteration much faster. Provisioning a cloud TPU effectively creates two resources: a TPU device and the VM that drives it. They must be in the same zone. If they're not, the configuration won't work. Whether you use the console or G-Cloud, the decisions are the same. Choose the project, region, and zone, pick the TPU type and size, then launch. The command line just exposes those choices as flags, but the underlying flow is identical. On accelerators, performance is only half the problem. Keeping costs in check is just as important. You can think of your cloud spend as a burn rate gauge, controlled with two levers. First, use preemptible TPUs for interruptible work like hyperparameter search or large-scale experiments. They're cheaper because they can be reclaimed, which is acceptable when you can restart jobs. Second, enforce shutdown or auto-stop policies, so idle VMs and accelerators don't quietly consume budget in the background. To connect TPUs to your data, start by setting up a secure command center. You authenticate with G-Cloud, work inside Vertex AI Workbench or a similar environment, and read or write data from cloud storage buckets. The core idea is IAM. Instead of granting your user broad permissions, assign a least privilege role, such as Storage Object Viewer, to the TPU service account. That lets TPU jobs stream training data and save checkpoints without exposing the rest of your project. XLA acts as the compiler that converts your high-level Python and framework code into a single, highly optimized TPU program. Rather than launching many small ops one by one, XLA analyzes the full computation graph, fuses compatible operations, and plans memory usage ahead of time. The result is a compact set of static instructions mapped onto the TPU's systolic arrays, reducing overhead, improving data reuse, and enabling very high throughput on large batches. TensorFlow and JAX follow different paths to the same XLA engine. With TensorFlow, you largely keep the familiar Keras workflow. You wrap your code in a TPU strategy scope, let it manage variable placement, and rely on model, fit to handle graph execution and replication. With JAX, you work in terms of pure functions. You explicitly JIT compile compute and use pmap to spread those functions across devices for data parallelism. A TensorFlow script targeting TPUs is really wiring together three concepts. First, initialization. A TPU cluster resolver locates and configures the TPU you'll use. Second, placement. Inside a distribution strategy scope, you define the model and optimizer, so TensorFlow knows these objects should live on TPU cores. Third, the data pipeline. Your global batch size becomes per replica batch times number of replicas, which is how you scale training cleanly across many TPU cores. With JAX on TPUs, organize your thinking into three layers. Start by calling JAX. .devices to confirm that TPU cores are visible. Then write a pure train step function and wrap it in JAX.JIT, telling XLA to compile that entire step into one optimized TPU program. Finally, apply JAX. 2pmap to shard data and run the compiled step in parallel across cores. This pattern only works well if your code is functional. No hidden Python side effects and state updated in an immutable way. You can view a TPU training run as an end-to-end pipeline. First, IAM ensures the right users and projects are authorized. Then, Vertex AI or your notebook environment becomes the control center where you launch jobs. Your TensorFlow or JAX code is written in a TPU-friendly style, so XLA can see clear tensor operations. XLA compiles that graph into an optimized TPU program, which executes on the TPU or TPU pod. Finally, checkpoints and artifacts are written back to cloud storage for recovery and reuse. When TPU jobs fail at compile or runtime, diagnose them by symptom. Shape mismatch errors usually mean the TPU graph lost its static predictability. Ensure all replicas use identical shapes and rely on padding or masking instead of allowing dimensions to vary. Unsupported ops are the other common issue. In that case, explicitly place that part of the computation on the CPU or replace it with a TPU-friendly layer. Overall, aim for static shapes and operations that stay within the TPU's supported set. On TPUs, telemetry is how you preserve your speedups. Start with platform metrics to check overall utilization and confirm that TPU cores are staying busy. Then use framework profilers to break each step into compute, data loading, pre-processing, and transfer. If data or pre-processing dominate, the TPU is stalling. Finally, compare this with your training curves. A smooth improving loss combined with high utilization usually indicates that the input pipeline is prefetching effectively and not wasting compute cycles. Scaling on TPUs works best as a three-step habit. First, validate. Run on a single device with a small, trusted dataset to confirm your code and configs before focusing on performance. Next, saturate. Tune input pipelines, batch sizes, and precision until each TPU is close to fully utilized. Finally, clean up and scale. Automate shutdown of idle resources, then replicate the validated, saturated setup across more cores or pod slices to approach near-linear scaling.